Had a question on Chapter 7, Problem 9. The problem says a 1,000-kilogram car pushes a 2,000-kilogram truck that has a dead battery. When the driver steps on the accelerator, the drive wheels of the car push against the ground with a force of 4,500 newtons. Rolling friction can be neglected. What is the magnitude of the force of the car on the truck? And what is the magnitude of the force of the truck on the car? And so let's look at this. So this is a common problem that we'll have. And I'm going to try to draw a car and a truck here. So here's my car, and so here's some big truck. And again, this is Chapter 7. Bad 7, sorry. Chapter 7, number 9. Now in this problem, what we're told is that the wheels apply a force of 4,500 newtons on the ground. Well, by Newton's third law, okay, that means the ground applies a force of 4,500 newtons on the drive wheels. And let's just say that the car has front-wheel drive just to make our life easier. And so that's the force that's acting from the ground onto the car. And it's very similar to when Dr. Harlow had his biking class and showed that when he spins the tires, okay, it's static friction that's moving those tires forward. And so this problem wants us to find something out about the force in between the car and the truck. So in a problem like this, where there's more than one object, this is typically what I do. So I start off by looking at the objects together, so treating them as one big object. And I believe the masses here was 1,000 kilograms for this guy and 2,000 kilograms for the truck. And so if we treat them together as one big object, all right, the force is acting on them. What are the forces going to be? Well, there's going to be a normal force of the ground acting up on the car. There's going to be mg of the gravity. So those would be the vertical forces. In the horizontal direction, the 4,500 is the only thing acting on those two forces. Right? We're told to neglect rolling friction, and so essentially we neglect any kind of friction that's going to be slowing this problem down. So if I look at these two cars together and I do Newton's second law, the sum of the forces equal, now here it's going to be the total mass. We're looking at both objects together. So the force acting is the 4,500 newtons, and that's going to equal the mass of 3,000 kilograms times acceleration. If I solve for the acceleration, I should get that it's 1.5 meters per second squared. Now that acceleration goes for either one of our objects. And so now I want to look at the objects individually. So I'm going to look at first the 2,000 kilogram truck, and I'm just going to draw it as a box. Just have to draw that all over again. Now what are the forces acting on this? Well, again, as we talked about, there would be the normal force, I'll call it normal force on the truck, and then there would be a downwards gravity, m of the truck, g. In the horizontal direction, now a lot of people want to say this 4,500 is acting on it, but actually that 4,500 is acting at the tire of the car. Okay, and what's actually applying a force on the truck is the car, and so we would call that would be the force of, I'll call it the car on the truck. So F of C/T. Again, there's no friction or anything slowing it down, so that's the only horizontal force acting on the car. So if we do F equals ma just on the truck, we should be careful. We're doing these all in the x direction, so the horizontal direction. This will be mass of the truck times A, and so the force we're talking about is the force of the car on the truck, and the mass of the truck is 2,000 kilograms, and the acceleration is 1.5 meters per second squared. When I figure that out, I will get a force of 3,000 newtons. Now, one thing that we can do, and so that's the first part, so I think that's part A. Yeah, part A was asking about the force of the car on the truck. Now, if you're doing this on a test, part B asks for the force of the truck on the car. Well, that's going to be the same thing because of Newton's third law. Newton's third law says that the force of the car on the truck, okay, is always, the absolute value of it is always going to equal the force of the truck and of the car. So they have the same magnitude, but they'll just be in opposite directions. So on a test, you want to sort of skip right to that and save time. But what we can do is just investigate this a little bit further to hopefully shed some light And so with the 1,000 kilogram car, if I look at the forces on that, draw a free body diagram for that guy, so it'd be a normal force of the car. We have the same thing, mg, mass of the car times g. You notice in this problem the vertical stuff didn't really matter to us. We also have this 4,500. So remember, that is acting on the car. And then we have backwards. So now there's going to be a force here. I'm sorry, that's a bad F. This is the force of the truck acting on the car, and that's going in the negative direction. And so if I write this out, F of x in the x direction equals mass of the car times A. And so you'll see here that F of x, my forces are, there's a positive 4,500 newtons minus the force of the truck on the car, and now the car is 1,000 kilograms times 1.5 meters per second squared. I'm not going to write my unit just because I'm kind of pressed in here, but this will work out to be 1,500 newtons when I divide that out. Okay, so it's 4,500 newtons minus F of Tc, and if you solve for F of Tc, you'll end up getting exactly 3,000 newtons. So you can solve for it, get the same thing, or just sort of realize from Newton's third law, but it's nice to be able to go through and check.